I would like to first thank the organizer for this very nice workshop. And I'm very excited to give this update on the parity violation on cosmological scales. So with this talk, I basically have two, say, main goals. So one is I would like to give an intuitive introduction about what it means by parity violation on cosmological scales. And at the same time, I would also like to give an update on where we stand on this topic, and especially since the theme of this workshop for this week is going to be the galaxy clustering. Therefore, I'm also going to be more focused on the 3D distribution of the galaxies. So with that, I have this very curious question I want to ask that this is photo taken by this very famous photographer, Benjamin Everett. This is a scene in southern Iceland. So I'm going to show two of these photos, and then maybe you can let me know what you think about it, like which is the original one and which is the mirror image one. So this is the first photo, and this is the second one. I'm going to play it again. This is first, and this is the second. Okay, who thinks the first one is the original image? There are quite a few. And who think the second one? Oh, wow, it's almost balanced. And who think it doesn't matter? Actually, it's a good that at least no one think it doesn't matter which one is which. So actually, it turns out the first one is the original image. And the reason is in photography, there's a concept called vision imbalance. And basically, when we look at the text or when we look at a picture, we want to start with the top left and to the bottom right. Therefore, it goes as this Z shape. So now if you flip it, you are not going to perceive it as symmetrically. So by the way, this is also something I learned new recently. Like when you take a photo, if there's some like a heavy object, you also want to move it slightly towards the middle of the picture just to keep this balance. But just from this example, I want to say that just how we perceive the world, and there's already like an asymmetry in the in this perception. But as we go to physics, we have encountered a lot of these symmetry problems, and especially coming to the parity transformation. So what I mean here is we have this spatial inversion of the coordinate that goes from the xyz to the minus xyz coordinate. Okay, so that's simple. But then before we move forward, we already have a second question that how can we extract parity information from scalar field? And especially given that we know a single scalar field doesn't really transform under parity. So there are many different ways to think about this problem. And here I'm going to take a shortcut that let's start by asking about the vector fields. Say, if I have a polar vector, if now I do a parity transformation, we know that it's going to flip the sign. Whereas if we have an axial vector, so this axial vector is built from the plane that is spanned by the vector A and also the vector B. And if we take the cross of them, that is going to form a normal vector to that plane. And that is also known as the pseudo vector. So the pseudo vector does not transform under the parity. So now if we put them together, have a polar vector and also an axial vector, that is going to give us a pseudo scalar. So the pseudo scalar in the form of R1 dot R2 cross R3, this object, it flipped the sign under the parity transformation. So that is also linked to this idea of using the tetrad to tetrahedron to probe the parity symmetry. So in this cartoon, what illustrate there is, let's say, if we sit on this vertex of the tetrahedron, and also look at its three sides denoted by R1, 2, and 3. At the same time, if we also range, the 1 is to be smaller than 2, than 3. And if we look at this vertex, it is going to like goes as clockwise. So this is like assigning an effective handedness to that vertex. So now if we do a parity transformation of this tetrahedron, we're going to arrive at this image. And at the same time, if we also look at this vertex, it is going to go as counterclockwise. So if we had replaced this exercise with a line or with a triangle, I mean, we can always do the parity transformation. But the thing is, with a line or a triangle, we can always rotate such that the transformed image is going to be overlapping with its initial image. And that's why for the scalar field, we need to have at least 4 points to probe the parity symmetry. And the reason essentially is because we want to build this three-dimensional objects that can embed this scalar triple product. So now if we want to open up the space, that while in this talk, I'm going to focus on the galaxy 3D distribution, but broadly, we could also classify the type of cosmological probes into the scalar or the vector or the tensors. And I also want to mention that in this afternoon, we are going to have a discussion session, and hopefully there we can go a bit deeper into more various type of these probes. But just very briefly, that maybe it's hard to see the colors in this projection, but the one that is in the darker color, for example, like the galaxy or the CMB birefringence, polarization, and even in gravitational wave birefringence. So these denotes the probes that currently we have some constraints using the real data. Whereas the ones that are in the lighter color, like the lensing or spin, etc., these are the probes that people have been thinking about and running some forecasts and got also some interesting results. So when it comes to what are the possible mechanisms that can generate parity violation? So again, there are many different angles that one can think about this problem. And also very briefly, here I will just take the simple approach and just group them into a early time mechanism and also a late time mechanism. And during the early time mechanism, one of the things that people have been thinking the most is about different inflationary scenarios. Whereas it comes to the late time mechanism, it's usually dominated by some dark energy or the dark matter model. And very typically, people think about those axion UN gauge coupling to explain the cosmic birefringence. And when it comes to the inflationary mechanism, and I'm also going to spend a bit more time on it just because I'm going to be focused on the galaxy clustering, and that's much easier to explain it with some primordial origin. So just over the past years, there had been these very nice papers by Liu and also by Kabas and stating about this no-go theorem, and basically says if one fulfills these different conditions, including the Bunch-Davis vacuum, scale invariance, unitarity, locality, and also if it stayed at tree level, then it's not possible to come up with a, say, the first principle parity violating mechanism. But given that there are these no-go theorems, there are also different efforts to make a yes-go. So these references, these are non-exhaustive references, but they are trying to break these different assumptions from these different angles. Cyril is not here, but for example, this is one of his work on try to use the, okay, Cyril, you are there. So this is Cyril's work on try to look for the Chen-Salmon gravity that produce a tree level signature to explain the parity violating mechanism. And if time allows, maybe I'll also give one example about our attempts and try to make the connection between the observable and also the underlying theory. Yes. So if you have multiple field, but then if you also fulfill all these different, say, conditions, then at least according to the Kabas paper, that is not possible, irregardless if you are single field or if you are multiple field. But then if you could break one of these conditions, then it is possible to generate that. Yeah. Yeah, that may be something really interesting also for the discussion this afternoon, because this is like from the theory paradigm that where we are. But if you go to the details, for example, asking what are the real conditions that we need to break in order to achieve this yes goal. For example, from this axion gauge field example. And you can ask whether it is breaking this no-go theorem because you go to the loop level calculation, or it is because you break the scale invariance. So from that point of view, especially in these cases, if you want to keep the statistical isotropy, then you would have to go to the loop calculation. So in a sense, you could also say, because you are going to the loop, and that's why you break the parity violation. But we could also come back to a real example and then just see like what are the source mechanism. Yeah, I mean, so these conditions, they don't need to be fulfilled at the simultaneously. So if you break one of them, then you can break it. So like in this example, several of them are actually from this cosmological collider program that you can show that if you have some exchange with some massive spinning particles at the tree level, then you can break parity. So depending on how you formulate it, so sometimes it could be due to the locality. Like in this paper by David Shi and Han Yu, I think what they did is they introduced some non-local operator. And according to that language, if you integrate those non-local operator, that could be corresponding to some massive spinning field. And in that sense, that breaks the parity. Yeah, so like in the Cabas paper, instead of putting the unitarity in the locality, they explicitly say that if you have a massive spinning field, that could break the no-go. Yeah. Okay. Guess we will continue. Okay, now let's come back to the 4-point function itself. So for the 4-point function, actually, this is a even more general statement that a function can be decomposed into a parity even and also a parity odd sector. So in the context of LSS, so this even mode would be induced by the nonlinear gravitational evolution, whereas the odd part is something we are excited about that could indicate some beyond standard model physics. And here in this form, that was also shown in the discussion by Fabian yesterday, that we can just make this very general statement and say that whatever happens to this odd sector, we could always factorize out the scalar triple product. Whereas this tau minus part, it denotes some even function that could only just have a radial dependence, but also even have angular dependence. So whatever that goes into this tau part, what is interesting is that there is this quantity over there. So in a sense, we could also reformulate this search for parity violation into what is the best choice of the basis that we can find for decomposing these 4-point functions. So I would list also these different criteria in terms of if we don't want to give up the statistical isotropy, then we want to have the rotation invariance. And at the same time, obviously, this basis need to be sensitive to the parity transformation. And at the same time, it should be fast that allow us to perform this calculation on millions of galaxies. So once we go through these different criteria, it turns out the spherical harmonics are just a very convenient choice. So first of all, if we take two spherical harmonics, they will span the vector space denoted by L1 and L2. And then from the tensor product, they can form a direct sum. And then we see that we actually got a chance to have the capital L, this combined angular momentum, to take a equal zero state. So that is a singlet. That is just like a scalar, doesn't transform under the rotation transformation. And then for a single spherical harmonics, it also, when we do the parity transformation, it will also bring this additional phase. And if this L is an odd number, then this basis function also flip the sign. And finally, regarding the speed and also factorizability, so at the moment I illustrate this with this cartoon, but I'm going to just explain it in the next moment. So just very shortly, when it comes to the basis of the 4-point function, so in the literature, it gets different names, like sometimes it's called the tripolar spherical harmonics, sometimes called the isotropic basis function. But basically, they denote almost the same object, that on the left-hand side, we have this curly P object that has the free angular momentum and also has the free unit vectors as the R1, 2, 3. And on the right-hand side, they are written as the products of free spherical harmonics and weighted by the 3J symbols. So they are constructed in this way because if we just recall how each spherical harmonics transform under the rotation. So there's this Wigner derotation matrix, and each of them will bring up the 3J symbol. So now we can take multiple of them, linearize them, and also apply the orthogonality relation. Therefore, if you just go through this step, you will see this will be the coefficient that eventually remain invariant after these transformations. So then how these spherical harmonics are essentially related to the galaxies. Let me use also this cartoon to illustrate this idea that we have this box to denote boundary of some simulation or surveys, and these particles to denote the distribution of the galaxies. And now we can just focus on these 4 galaxies, and with this to be the center, and also with 3 neighboring ones within radius capital R. And with their separation to be the R1, R2, and also the R3 vectors. So if we have a single density field, I mean, we can do a radial and angular decomposition where the coefficients here, this ALM, it's actually also very much in analogy with how people do the CMB analysis. Whereas this angular basis here are the spherical harmonics. So this is the example for a single density field. But now if we want to generalize this to n density fields, so we basically just take n copies of a density field and take their ensemble average. And by the way, this is our definition for an endpoint correlation function. But here we could also do the radial and angular separation with this angular basis to be the one that we just discussed in the previous slide. Whereas this radial coefficient is the quantity that is of interest that has the subindex denote this capital lambda with that just basically denotes the collection of L's, and then with the radial R coefficient. So now with this basis, it's very neat because it allows us to factorize this problem that before when we want to calculate the 4-point function, we need to calculate this quartet all at once. But now with this basis, we can factorize it into a pairwise counting that we can find the first pair, the second, and also the third, such that it largely reduced the scaling from a quartet counting, but down to a pair counting. So now if we imagine we want to apply this algorithm to modern galaxy surveys with millions of galaxies, if we don't do anything with the brute force counting, that can easily result in like 10 to the 24th number of galaxy quartet that will really translate into centuries of calculations. But now with this algorithm and also with some GPU acceleration that can really help us and to reduce the computation time down to just 1 minute. So that is, yeah, just much faster. Okay, so now we have this algorithm that is working, and I just want to show some visualization of what does it mean by having a parity violation on density field. So here are some simulations that we constructed, and because we construct the simulation, we also know how to subtract the noise for the Gaussian random field, then we can just focus on the non-Gaussian part of the simulation. So here what we inject is this template that is at the cubic order. So what is interesting to notice is that probably you can see these helical or these vorticity structure that are imprinted on the density field. that would otherwise not exist if we just run a standard n-body simulation, follow the Newtonian gravity. And now seeing this density field, we also want to extract these features from the density field. And that connects to this measurement of the odd 4-point function coefficient from these simulations. So here in the upper panel, I'm showing the arrangement of these coefficient and as a function of the index for the tetrahedron configuration. And here I'm also choosing this L's for the L1, L2, L3, they all equal 1. Whereas in the lower panel, I'm showing the arrangement of the 3 radial beams for the R1, 2, and 3. So when running the simulation, we also prepared 2 sets of coupling constant, and one is positive and the other one is negative. That's why we see there's the blue and also the red curve, they oscillate out of phase. One interesting thing to notice here is that we see they kind of show this fishbone shape. And the reason is because the template we injected into producing this simulation, they are at the so-called squeeze limit. So basically means one side of the tetrahedron is much smaller compared to the rest. And then because of that, if now we fix like R1 and R2 and then increase the R3, that is like more approaching the squeeze limit. Therefore, we see that there is an increase in the signal to noise ratio, but then it drops back once we exhaust the R max of R3 and making the 1, 2, 3 become similar again. And this pattern just go on and on until we go to the other end. Once the 1, 2, 3 becomes comparable again, there we see there's a drop in the signal to noise ratio. So these are like one possible feature that it can imprint on the 4-point functions. So at this point, I mean, this is quite interesting, but we maybe also want to like do some brainstorming and ask whether we can find more features imprint on the odd 4-point function. So that brings to one of our favorite object in galaxy related to the BAO. So I guess everyone here knows what BAOs are. So they are basically these primordial sound wave that can leave imprints at some characteristic scales. So in the past, they have been used as a standard ruler and to probe the expansion history. But if we think about the BAO, they actually modulate this entire density field. So in principle, they could also leave imprint not only on the 2-point function or 3-point function, but essentially also on the 4-point function and even in the odd 4-point function. So if we could measure the BAO feature from the odd 4-point function, that could in principle also give us an additional validation of saying whether the 4-point function itself is from some primordial origin or not. Then based on this idea, we just run some simulation and to show this proof of concept that in the middle panel, this is a measurement from the simulation that has the BAO wiggle. And on the right-hand side, these are the simulation that has no BAO wiggle. So by eye, it's really hard to tell their difference. It's also not kind of surprising just because we know the BAO is like a 1% feature. And we don't really expect to see when we plot these coefficient on the 2D, then we can pick out the difference just by eye. However, if we take their difference and look at the residual between these two configurations, then we can see that on the left-hand side, this residual is indeed non-zero. So this is just to demonstrate that in principle, we could have the BAO also imprint on the odd 4-point function. That would be very interesting to continue to search in the future data. Yes. Yes. So yeah, this is actually a very good and also subtle point that so if there is no parity odd signal, then BAO is not like imprint on anything, but rather what we're going to see is just some statistical fluctuation. On the parity even trispectrum, yes, definitely. Yes. Yes. So so first of all, when it comes to the measurement of the even and odd, we can separate them clearly. We can look at the combination of these L to be an odd part or to be an odd combination that only separate or isolate the parity odd information. And on top of that, if there is a BAO imprint, then we are going to see a higher fluctuation compared to, or higher, say, significance compared to the one that has no parity violating mechanism. Okay, so far I've been talking about what we can do about the 4-point correlation function. But here we could also ask that, is there another way to think about how to extract the parity information from the scalar sector? So here maybe let's also do a quick review about what are really the necessary ingredients such that we can make the estimator itself to be sensitive to the parity transformation. So we talk about we need to have 4 fields. We need to have this scalar triple product. And when we combine these like 2 different ingredients together, that is essentially a different statement of saying that how we can like a group and also reweight these 4 fields. So on the one hand, if we just take these 4 fields as they are and take the ensemble average, this is just our usual standard definition about the trispectrum or the 4-point correlation function. But alternatively, we could also take 2 fields and do something to them, and take the other 2 fields and also do something to them and glue them from the middle. Another option is we just take this single field as a bare field and then do something to the rest of these 3 fields. And these 2 corresponds to some form of the compressed 4-point statistics. And that is lead to this idea about this so-called parity odd power spectra as a different estimator we proposed last year. That the idea here is we want to cross-correlate a vector and also a pseudo-vector. So in the beginning of the talk, we discussed that a vector transform as parity odd and a pseudo-vector transform as parity even. So if now we put them together, that can give us a power spectrum object, like from outside, but it also transform as parity odd. So this is like quite interesting and also a little bit counterintuitive. But essentially what's going on here is both of these vector and also these pseudo-vector objects, they're essentially the composite field. Therefore, intrinsically, also this power spectrum encodes information about 4 fields and also including different weighting of these 4 fields. And I would also like to mention that like back already almost 13 years ago, there had been this very nice paper by the group of Jean and Kamilkovsky. And that time they proposed this idea about the clustering fossil. So although from the first glance, the fossil and also this pop picture, they look quite different. But if one lay out the math calculation, actually we can find several like one-to-one correspondence between the fossil and also the pop. And moreover, this also shares some similar concepts in terms of building the compressed statistics like skew spectra, curve spectra, and so on. And also I want to mention here, like in Azadeh's group, the postdoc Zhu Shen is also currently looking to this pop and also apply them to the late time density field, and they're going to have very interesting results upcoming. And one more thing I personally like a lot is to make this a little bit detour and see what are the connections between pop and also those polarization states. So on the one hand, if we have just a very general vector, we can do the Helmholtz decomposition to have a curl-free part and also a divergence-free part. And moreover, for a general vector field, it also has 3 degrees of freedom. That has a 1 longitudinal degrees of freedom and also 2 transverse degrees of freedom. And these 2 transverse degrees of freedom, they correspond to the polarization state. So now if we do the cross correlation between the V and also the A field, and we'll find that they are proportional to the coefficient of the cross correlation for the polarization basis. So in that sense, I just find it very neat because when thinking about the polarization, usually we think about photons or gravitational waves. So although like here in this talk, I've only focused on the galaxy distribution and they're completely different physical objects. But nevertheless, here we can see there are some like indirect link in these formalisms. Okay, given that, I also want to show a measurement of the pop to the simulation. And here we prepared two different sets of simulations. One has the parity violating mechanism, and the other one is just in Gaussian random field. And that is shown in the red and also the gray points. So first of all, there's a quite clear distinction between the red and also the gray, which shows that if there is parity violation going on in the field, then the pop is able to pick out this information. And moreover, seeing the good agreement between this black theory curve that goes through these measurement point also shows we have a reasonable understanding about this new estimator. Any questions so far? If not, I'm going to move to the real world. Okay, now let's talk about the real world, about when we apply these 4-point function to the real galaxy data. So when it comes to the real world, we have to worry about many things. Potential signal, systematics, cosmic variance. So very often we are also interested in quantifying detection significance. And also very often we use this chi-square statistic and with no hypothesis. And essentially what we care about is, say we have this no hypothesis distribution and say, if we want to just say there's no new physics, if the signal is zero, then this is what we expect for the distribution. And here's our test statistic. And then we want to look at what are the area covered by this null hypothesis. And we translate that into a detection significance in the unit of sigma. So based on this principle, we apply this measurement to the BOSS data from the Sloan Digital Sky Survey. So that was a telescope located in New Mexico. And on the left panel, this is the measurement we apply to the data. And first of all, I want to guide your eye to this black histogram, which shows the simulation that has no parity violating mechanism. That give us kind of a reference of if our universe is just as what we expect, then where is the center and also what is the width of the distribution. Whereas this orange vertical line denotes the measurement from the real data, and then the separation between the two indicates the detection significance. So back then, on one of these SDSS data, we found a really high detection significance, almost reaching 7 sigma. So that was like a really interesting, also a very intriguing measurement that triggered a lot of follow-up study and also a lot of discussions. So back in the paper, we also did a lot of study in terms of understanding what are the systematics and also whether systematics could contribute to different levels. But just as a very short summary, that what we understood from at that time was that it's actually very hard for systematics to produce a parity odd signal. Whereas what is less or much more unclear is how systematics could contribute to our understanding of the error bar, or namely the covariance matrix. And based on that, we also tried different approaches just to push this question. That's why we had the development on using different estimator and also try to see if we can make more direct connection between the theory and also these measurements such that we can more focus on some physical degrees of freedom that are, for example, predicted by first principle theories and to reduce the redundant degrees of freedoms. And a different approach to move forward is just to simply look at a new data set. For example, here we are all pretty excited about the dark energy spectroscopic instrument. And here on the left-hand side, this was a photo I took earlier this year while I was doing an in-person observation. And here's the housing for the DESI instrument. And here are some beautiful city light from Phoenix, although pretty useless. So the DESI, it is a fiber fed system, so which basically means that it tried to use fiber to collect light from galaxy and then convert that into a redshift. So here we could also see there's the focal plane of DESI, and here are some cool animation shows the movement of the fiber robots on the focal plane. And so this is a footprint of the data release one that basically collects the first 13 months of the observation. And so far, DESI has been the largest SPEC survey that has collected about 5.7 million galaxies and also the quasar spectra. But then if we look at this footprint, so this color coding denotes the completeness. And basically, these are the defined as, if we look into one patch, if we expect to see there's n galaxy, but in fact, if we only measure, say, x galaxy, then this ratio denotes the completeness. But here, there's a huge variation in the DR1 data release, where for the redder color, that means it is almost complete, but then that can go down as to this blue area that is like a 10 or only 20%, whereas these gray parts, they're not even observed yet. So my current conclusion from this sample is that this sample is really great for analyzing, say, physical quantity with very high signal to noise ratio. Whereas if we want to look at some quantity, such as parity violation on this sample, actually it is very, very difficult because we need to be very careful about many sources of systematics and also their induced error bars. But before we move to the parity odd sector, I just want to very briefly mention this check on the parity even sector. So as we mentioned before, that the 4-point function could be decomposed into a parity even and also a parity odd component. And in this case, the parity even part, and especially these connected 4-point function, are induced by the nonlinear gravitational evolution. And they are diagrammatically represented by these 4 points and combining different combinatorial ways. And in this upper panel, I'm showing the measurement of the coefficient for this L combination of 2 and 4 and 2. So basically, the takeaway message from this plot is that for this specific channel, we have a pretty good agreement between the data and also the simulation. And also, it's pretty clear that the signal is not vanishing. And on this sample, we also tested like a different methods in terms of quantifying the detection significance, but we also consistently found there are more than 14 sigma in terms of this gravity-induced even 4-point function in the DESI DR1 sample. So we did this because before we apply to the parity odd study, we do want to validate whether this method we're going to apply makes sense or they work. Therefore, we want to take some signals that we have a much better idea on. But now if we want to move to the parity odd sector, the story is quite somewhat different because now they are going to be dominated by noise. So for example, if we look now on the right-hand side, these are just some examples of the measurement of the coefficient. So here it's really hard to say if we see any like a distinctive features, but rather they more or less just oscillate around zeros. And moreover, here we also need to worry about the additional contribution from systematics, and they can contribute both deterministically and also stochastically. So next, I'm just going to show that if we don't do any calibration, just naively apply the measurement, and this is what we are going to get. So this is a similar plot as we saw before, whereas this vertical line denotes the measurement from the data, and then these different histograms denotes different type of simulations that are available in DESI DR1. So we see that they pretty much scatter around, and that is because there are two major effects coming into play in terms of the covariance matrix. So one of them is the sample incompleteness. We saw this huge variation in the density field due to the limited number of fibers. And the second effect is because more like the limitation we get from the simulations. Basically, the n-body simulation we use for DESI, they only have 2 gigaparsec volume on site. Therefore, in order to embed this entire DESI survey in these simulations, so what people did is to like just replicate those boxes such that they in total make a much larger box. However, by doing so, we really don't gain independent K-modes. Therefore, if we look at the covariance or look at the variance of this measurement, they're going to just much overestimate this fluctuation. And that is the reason why we see like from these abacus marks, they have higher fluctuation, whereas with the easy marks, they have a lower fluctuation. And there are also two like different implementation of the fiber assignment scheme. And one of them is a approximated method. The other one is more realistic, but that also brings more statistical fluctuations. So therefore, like even before we do anything real, we just need to first worry about the calibration of these simulations. So after doing the calibration, now we can see they pretty much agree with each other and all just centers at the place we expect given by the number of degrees of freedom. And also from this preliminary study that in this autocorrelation of doing the chi-square, there is a 5 sigma detection significance. So by the way, I also want to mention that there is an additional group also performed this analysis on this sample. And from this point of view, and there is pretty much good consistency between the group. But here we could also ask that how much do we trust this result? And how well do we think we have a good understanding about the arrow bar? So therefore, we continued also to carry out this cross correlation as a consistency check. So basically, the idea is that if we have some underlying signal, then we expect them to oscillate coherently. Either we look into the northern sky or in the southern sky. Whereas noise, they do not correlate. Therefore, if we do the cross correlation between the signal, the noise is going to drop out, but we can pick out these deterministic contributions. So here I would also like to point out that while during our BOSS analysis, we also did a similar study like this cross correlation, but it was really these people led by Krolewski in the group of Kendrick Smith. They did a much more careful study of this cross correlation and gave a lot of improved like analysis in the details. So in terms of the cross correlation, the picture quite much inverted that instead of a 5 sigma, but rather here we're seeing the signal becomes pretty much consistent with zeros and even move towards the negative side. So that brings up the question like, is like there a tension in these two analyses? I just want to say, no, there's no tension. And what one should actually also check is how much does the data and the simulation, they agree in terms of their stochastic contribution. So there's actually another type of cross correlation one could compute that was also proposed in the paper by Krolewski et al. That one could explicitly calculate the difference between the measurement from different patches and cross correlate them. And that allows us to pick out the stochastic contribution. So here on the left, on the right, the difference between this histogram and also this vertical line shows us how much is there a disagreement between the data and also the mark in terms of the fluctuation. And we can then use this difference to further correct for this autocorrelation plot we saw on the first slide. Therefore, we are going to see this solid line is going to now shift it towards the left. And then that is also becoming consistent with zeros. So in a sense, I just want to say that there's no tension in different analysis methods. That is totally as we should expect. And my another takeaway is it is actually very hard to analyze this DESI DR1 parity odd sample. And personally, I very much look forward to repeat this for the DR2 and also once we have a much more complete samples. For example, if we just take the reference in terms of comparing the BOSS and also for DESI, like back in the BOSS time, the completeness is above 95%, but right now we are not even close with this first year sample. Yes. Yeah, so to some extent, the effect of the fiber collision is also corrected for when I compute the data sample. So one of the effects of this fiber collision is that if one use this approximate method, it is going to underestimate the covariance. Therefore, when we compute the data points and using those approximated marks and also combined with some analytic template, and that part is going to underestimate the covariance. And therefore, if I don't do any correction, then the points, or actually this line, it is going to be further shifted away from zero. And this part I correct for in that sense. And moreover, we could also compare, like in this plot, this solid curve, it is not a Gaussian distribution, but it's rather computed by taking the variance of the cross statistic, and then we can overplot it over the simulation. And then you can just see that the distribution of the simulation and some theoretical prediction, they agree with each other pretty well. Yeah. That was actually done in the Krolevsky's paper. And in that sense, they do found there is a mismatch between the data and also the simulation. Yes. Okay. Yes, Matt. Um, yeah. I guess these simulations should represent the spirit of a no test for the data. I mean, for the data, yeah. Um, that's a very interesting idea. Yeah. Yeah. Yeah, so we have also thought about whether we can just take this like image and then flip it, but there are several like technical details are actually very hard to do it fully correctly, including how we calibrate these weights, and also once you have these weights that are coming from like a multiple iteration of construction from imaging and a spec, and that is also folded into the random. So now you want to have calibration of some random distribution of particles that doesn't know about the clustering. And then you also want to fold the weight on this random distribution and use that to correct for your real observational data and then form that into a density fluctuation and then do this exercise. Yeah, we thought quite a bit about it, but we haven't got a really clean way of doing that. I mean, if one think about, maybe I shouldn't say this is so fair, but maybe with CMB that's a bit easier or maybe cleaner to do. But with in this case, yeah. Okay, I guess I will just use my last few minutes and then going to give one live example about how, for example, we can see the connection between some underlying theory and also the galaxy observable. So like in one of these examples, like the axion and U1 gauge inflation model. So here is again some very incomplete reference of the list. But in the past, people have been thinking a lot about these models. And also last week, we also heard the talk by Lorenzo discussing this model, although more in the context of the dark matter. So like in this case, if we have this Chern-Simon coupling term, then this background evolution of the inflaton field can make the particle prediction and that inverse decay into the inflaton fluctuation. And basically, these two equations of motions are of our interest, that on the one hand, this gauge field has two branches, has the positive and also the negative branch. And as they evolve, they break the symmetry. Like one branch is going to get announced and the other one is going to get suppressed. And to some extent, you could also say the parity symmetry is maximally broken for this gauge field. But then they also source these inflaton perturbations. Therefore, that kind of transfer this information about parity to the inflaton fluctuations. So in the past, there had been also group by Wei Xue, and also led by Niu et al., and carried out this computation for a primordial curvature trispectrum. So basically in this integral, here you have some Green's function, polarization state of the gauge field, the mode function, and also different Dirac delta functions to impose the momentum conservation. But this is also a very high dimensional integral, and if one just want to carry it out, that takes a lot of time. Therefore, in this paper, they just pick out some specific configurations to evaluate for the trispectrum. Therefore, one thing we thought about is, can we simplify this calculation? And one way to look at this is basically we want to reduce the angular structure of the integral. And they arises from these vertex. For example, we have the momentum conservation that corresponds to this convolution structure that encodes the angular information. And the polarization state of the gauge field, they also have the angular information. And moreover, when we have the weight contraction of these different legs, they also lead to the Dirac delta distribution that also again have the angular information. So basically, with a student at UF, we carried out this reduction and did this very brave calculation that in the end, this is what we arrive. I mean, although this is still a very long equation, but mostly these are just some phase and some coefficient. And then the most useful dynamics is encoded in this curly T symbol, but that only has the radial dependencies. So that would be one example that could be very interesting that we can forward model it to make the connection between the galaxy observable of nowadays and also some primordial inflationary signals. And moreover, there have been recent developments in this axial lattice simulation in the MPA group, like by Angelo Caravano in the initial paper, and then also recently improved by Drew Jamieson. So this lattice simulation will also be like really interesting and also really helpful that if we could also forward them and then to adding the impact of a gravity and also various observational effects, then we could also make a more direct comparison between the theory and also the data, and also help us to check several of approximations that went on in these analytic calculations. Okay, I think I'm almost at the time. I just want to make two quick announcements. So this year, we also have the Parity Violation from Home conference. It's a surprise that it's already a fourth edition for this online conference this year. So for any of you who are interested, please follow this link for registration. And the conference itself will take place from 18th to the 21st of November this year. It's going to be fun. And the second is I'm going to very soon start a hermeneutic group at LMU. And if you are interested or if you know someone who are interested in postdoc or PhD positions, please let me know. I very look forward to that. And with that, thank you for your attention. Yeah, so it is simpler in a way that we can reduce the dimensionality by a lot. So that was essentially one of the motivation. So actually the pop is very complementary to the 4-point function, because in a way that here I'm only showing one type of pop, which is actually similar also to the galaxy shape or intrinsic alignment discussed in Fabian's talk yesterday. That is like you cross-correlate kind of two power spectrum-like projects, but that is modulated by a long wavelength mode. So in a sense, an intuitive picture is that this pop is going to be sensitive to those like a collapsed type of tetrahedra. Whereas something I didn't show is this second configuration. So we call it as the scalar pop, because here we are cross-correlating scalar and also a pseudo-scalar. So in that sense, it is sensitive to those like a squeezed type of these templates. Whereas for the galaxy 4-point function, our current understanding or like intuition is that it is more sensitive to those equilateral shape, just because once you work with those compressed statistic and by taking the derivative, you inevitably will bring terms that is like a k or diagonals of a k1 and k2 to the minus some power, such that it's very easy to push them into a squeeze or the collapse limit. Whereas for the 4-point function, you just take them as bare field and project them onto an angular basis. In that sense, you don't really necessarily drive them into those squeeze or the collapse limit, but rather could be sensitive, for example, to a complementary template. But then, okay, I drive away a little bit, like in terms of a complementarity. But then the POPs is indeed, it reduced the dimensionality. And that is one of the reasons we wanted to develop it at first. But there is also a question, for example, how do we deal with the window function? That if we want to follow like similar methodologies, like how people deal with the power spectrum, bispectrum, and then if we don't come up with a good, say, mode to mode correction, then the POP is going to be affected by the window function and coupling different scales. And that is one thing we try to think about for this correction, either correct it at the estimator level or think about when it comes to the theory model, how can we like do the window deconvolution? And moreover, another thing is about the noise part. So that part, maybe once Azadeh's paper is out, that would be very interesting to see it as well. But at the current, my understanding is for the POP. So for example, if we look in the Fourier space estimator, we're going to be affected by the shot noise. And there's not really effective way for us to isolate the bin such that we can explicitly exclude the shot noise. So while I do not think the shot noise would be picked out by the POP construction just because it is targeted at a parity odd, say physical quantity, but the shot noise is not. But nevertheless, it can play a big role in terms of increasing the statistical error bar and decrease the signal to noise ratio. Yeah, 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 yeah. Yeah, yeah. So the current intuition is that CMB and the large scale structure, they could also be very complementary, because if we really think about in the small scale limit, especially that could be very clearly see if you do the spherical harmonics expansion at the infinite high L limit. And there it is going to reduce to just a Legendre polynomial. And with all the m's kept to be zero. And in that sense, if you want to form the 4-point function, that would just give you a Wigner 3J symbols with all the m to be zero, and then you will force it to be a parity even quantity. So that is kind of matched with the intuition that if you have just a plane and you cannot build this scalar triple product because everything is just on the 2D plane. Therefore, for the CMB, it's much more advantageous if you go to the larger scales. Say you have these modes embedded in the curve space, Whereas for the galaxy, like for the scales that we are probing currently is around like a tenth or not really much more than like 100 megaparsec. So in that sense, it is at a much smaller scales. Therefore, if I again like put in this template thought, I would say galaxy is probably at this current configuration, it's more similar to the equilateral shape, whereas for the CMB, it's probably better for those squeezed or the collapsed type.
Yeah, so when you said that early on that the demand of the third century, so what exactly was that? So that is like an estimate of
The 4-point function itself, say, yeah.
all.
So if I want to compute the same 4-point function, and instead of doing this acceleration with GPUs and this algorithm, blah, but I just say I sit on one galaxy and then count there are three galaxies nearby, and then get this coefficient. Don't do any decomposition, and then move to the next galaxy, and that is going to take almost centuries. So. So in total, so if I just do the very same comparison for the plots that I show later for, for example, for this type of plot, so we had a summer student who really did a great job and tried to just say, instead of using these spherical harmonics, but rather working in a Cartesian coordinate, but without doing this decomposition method, but rather just take one galaxy and then decompose it into different Cartesian coordinate and then with some GPU acceleration. And we didn't finish that summer project because he did a projection that it would take like, for the 3-point function, it would take like decade. And yeah, and then, yes, we definitely think we need to accelerate. So then we made a different modification to that summer project. But that was the extrapolation from there.
That also goes
Yes, yes, yeah. Because it is again built on the similar intuition that we need to have a kind of a 3D structure. Whereas for the systematics, just very broadly, if we think about it, so okay, maybe I could say that there could be, for example, the source because of how we handle this algorithm that can be counted as a systematics, or there could be the systematics due to how we observe the universe. So in that sense, for example, maybe last year there had been paper looking at the relativistic effect and then found there could be a parity odd mode for the trispectrum. But many of these RSD or relativistic related effects, they are actually defined with respect to the line of sight. So if now you want to do the average over all the line of sight, and those odd multiple terms would just drop out. Whereas when it comes to the observational systematics, and many of them are, for example, imprinted on a 2D image, and that does not have a direct coupling to the 3D radial selection. Although there are some like exceptions, for example, this redshift failure effect, where when you drop out the galaxy, that could also be modulated not only on the 2D plane, but also dependent on the redshift themselves of the galaxies. But like in those ones, we played around in the Bose sample that we artificially throw away additional galaxies according to their color cuts and to mimic the redshift dependence. But by doing so, we didn't find that was able to totally remove the signal. Yeah. Yeah, so I mean, this could totally be one possible effect, but that is kind of a follow the similar spirit as this redshift failure, for example, how you can have a 2D mode, but that actually has the say the correlation in the radial direction. So I guess that if I think if one and a half like probably the method around if they're over galaxies that are coming from different directions, but they also are essentially in the direction they can get clustered. Yeah. There are things that the direct system survey will not think about the regular different. Yeah, I think these are really like interesting question. I wonder like if we could formulate this as something general that if we would, for example, think about, okay, maybe if I put in this way, that if I had no understanding about my galaxy selection, but if I just mix two different of galaxy samples, then for example, in Pat McDonough's paper back many years ago, they could already show that even for the power spectrum, you could already generate a parity odd sample. But in that case, it is like explicitly cross-correlating two type of galaxies with different bias, such that their cross term does not cancel at the bias level. That's why you have the odd contribution. So I guess in the example that you were giving, it's maybe in terms of a bit analogy that if I do not know what are the intrinsic galaxy property, but then I just do some mix, and then can that leave some, say, imprints on the statistic that we observe? And maybe that is also a bit related to Stephen's question about the extinction. I need to think more about it, sorry. Oh, covariance matrix, that's one of my favorite topics. Yes, it is a Gaussian covariance matrix, but I just dropped. Let me see if I have. Yes, yeah. Then probably I do not need to show the slides. So yep, that is based on the Wick theorem, and then we just expand these 4 points. Yeah. Yes, after the correction, it looks like all these excess in the significance would go away. Actually, not by me, but by Phil Cox. He has several series paper on this topic, both into temperature and also polarization. So these are really interesting work. No, so far there is no detection yet, but that is one thing we would like also to discuss this afternoon, because there could be several interpretation in terms of the model, the estimator, and also like how you construct this optimal estimator and what are the possible loss of information once you do the coarse binning. But then that would again like fall back to the question whether your signal has some like intrinsic oscillatory feature or maybe they're just smooth and they could lose information or maybe not lose information in different form.